Okay, so what we have is the dual problem. The dual problem. Okay, so I'm going to call the problems that we have been looking at so far, I'm going to call those type of problems the primal problems. So primal problem. So primal problem is basically be whatever LP is trying to solve. Okay, so let's say I have an LP where I am trying to maximize the objective function z, which I am going to express as f of x. Okay, x is the vector of decision variables, and subject to, I'm going to write the matrix form of the constraints. I have matrix A, which is m by n, multiplied by x, which is n by 1, and this is less than or equal to some vector of constants b, which is m by 1, and of course together with the vector x larger than or equal to 0. So what is the meaning of x greater than 0? It means each variable x1 up to xn. How many variables? Let me actually write down how many. Let me actually write down x1 dot 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 xn. The decision variables are non-negative, right? So whatever problem you have at your hand, you're trying to solve, I'm calling that the primal problem. And now, associated with a primal problem, there is a dual problem. And the dual problem, in the dual problem, you are minimizing certain objective function w, which I'm going to call g of y, and subject to constraints, where I'm going to express the constraints by saying it's a matrix B. Now the matrix B in the primal problem, the matrix dimensions are m and n. Here it will be the opposite. It will be n by m. And then the vector, the decision variables in the dual problem, there are m of them. Okay, so this is m by 1. All right, and this would be larger than or equal to some constant vector d, and d would be n by 1. Okay, and also the decision variables y1 up to ym, they are non-negative. So this would be the dual problem. I haven't told you what it is. We are going to see what this is hopefully at the end of today. So this is the dual problem. Is everybody okay? Again, I haven't told you what the dual problem is. We are going to try to find out what that dual problem is. Now, what's the idea of the dual problem? Let's just foresee that. The idea of the dual problem is, let me use arrows here. Okay, so in the you have in the primal problem, what do we do? In the primal problem, we start with in the primal problem. So here I'm looking at the primal problem. You start with a sub-optimal value of Z. Remember, when you come up with the first feasible initial dictionary for the primal problem, the value of Z is suboptimal. Right? It's not the optimal yet. So what do? You start with the suboptimal value, and then you increase Z until you obtain the optimal value, right? So increase, and you try to increase Z until Z star, the optimal value Z star, is obtained. Am I making sense? So let's say here is a suboptimal value of Z, and then you keep increasing the Z value until you get to that optimal value Z star. So here I am speaking about the primal problem. The idea of the dual problem is that we want the solutions of the dual problem to give you upper bounds for Z star. Is that making sense? So in the dual world, what we want is that the values of the objective function, we want that to be an upper bound for Z star. We want that to be upper bound for Z star, and so you're basically starting with an upper bound of Z star, and then you decrease W until Z star is obtained. Let's see if that makes sense. So here we are start with upper bounds for Z star, and so basically you're going to obtain a optimal value for the objective function of the dual problem, and that's going to be the same as the optimal objective value for the primal problem. Am I making sense? So what I'm trying to do is I'm trying to find the problem, which I'm calling the dual problem, and I want solutions associated with the dual problem to be upper bounds for Z star. So instead of increasing value of Z to get Z star, we are decreasing the value of W in order to get Z star. Am I making sense? Again, all this, I haven't told you what the dual problem is, but I'm trying to tell you that what's the motivation for the dual problem. The motivation is that we are going to do dual problem will give you upper bounds for Z star, and then if you keep decreasing the upper bounds until you get the least upper bound, okay, which is W star, and hopefully that's going to be Z star, and then we can obtain Z star in that way as well. Is everybody okay? But the question though is, how are we going to get upper bounds for Z star even without knowing Z star? Am I making sense? Without knowing Z star, how am I going to find upper bounds for Z star? How would I know upper bounds for Z star? So let's try to do some examples to understand what we may be able to do to come up with upper bounds for Z star without knowing Z star. Is my discussion clear to you? Okay, let's look at an example. Let's say I am trying to maximize the objective function z, which is x1 plus 2x2, and subject to certain constraints which are negative 2x1 plus x2 less than or equal to negative 2. Let me turn off one of the lights here. And x1 minus 2x2 is less than or equal to negative 2. X1 less than or equal to 4. X2 less than or equal to 4. And of course, the non-negativity constraints are there. My question to you: can you find an upper bound for the optimal solution z star of this problem? Am I making sense? Do you understand what upper bound is? Whatever z star is the optimal solution, optimal objective value is, I want a number bigger than that. Can I come up with a number bigger than the optimal objective value here? That's my question. Is this clear? Now, what's the idea? Well, what is the objective function? The objective function is x1 plus 2x2. So basically, I want to come up with a number which would be bigger than any objective value, right? So I want this function, objective function, bounded by a number. How am I going to get there? Well, the idea is that let's work with these inequalities. And by applying some elementary operations to these inequalities, can I isolate on the left-hand side x1 plus 2x2? Is that making sense? Can you isolate? The objective is x1 plus 2x2. If I can isolate x1 plus 2x2 by using these functional constraints, then I would be able to get a bound, right? Am I making sense? So let's see if I can. Can anyone see how I can get? Let me also specify here the optimal solution for this problem is that z star is 12 and it happens at 4, 4. We did this problem some couple of days ago, okay? So z star is 12 and the solution happens at 4, 4. The optimal solution happens at 4, 4 and the optimal objective value is 12. We don't need to know that for this problem. What I want to do is I want you to think about how you can combine some of these functional constraints so that you isolate the objective function on the left-hand side and the right-hand side is a number. Am I making sense? Can you think of any way of combining these constraints and so that you have the objective on the left and a number on the right? So these are less than or equal to always, right? So when you get this on the left, the right-hand side will be some number, so you get a upper bound for the objective function. Okay, can you think of any combinations, any way of combining these inequalities to get the objective function? Anybody? Yeah. Say it again. Third one time. So what he's saying, add the first one to twice of the fourth one, right? Let's see what we get. So if you multiply the third one by 1, you get x1 less than or equal to 4. And if you multiply the second one by 2, right, you get what? You get 2x2 less than or equal to 8. So now together, when you add them, what do you get? x1 plus 2x2 less than or equal to 12. So that tells you what? That tells you z is less than or equal to 12, no matter what x1 and x2 is, right? Am I making sense? So this is an upper bound. So I obtained an upper bound w for z. Is that making sense? So what I'm going to say is that the way I am obtaining it, I am adding the third one to the fourth, twice the fourth one, and getting this bound. Is that the only way? Can anyone else think about some other ways? Can you get an upper bound for z in another way? Any other way of getting an upper bound? Is there any other way of getting an upper bound? Any other ways? Very good. So so what he's saying, multiply the fourth one by 4 and add it to the second one, right? So let's see what happens. When you add it to the second one, the coefficient of x1 doesn't change, right? And then you are adding 4x2 to negative 2x2, right? So 4x2 negative 2x2 will give you what? Plus 2x2. And then less than or equal to, you're multiplying this by 4, so 4 times 4 is what? 16. 16 plus negative 2, right? 16 plus negative 2 is what? 14, right? So then again, I am getting that the objective function has the upper bound 14, right? Is everybody okay? And there are multiple ways of getting an upper bound. My point is, the point that you want to have here is that how did I get the upper bound? The way I got the upper bound is that I multiplied each functional constraint by a constant and added them together and got the objective function less than or equal to some number. Is that making sense? Now, why did I say I can multiply each constraint by some number? Well, I can think of this second solution that David gave. I can think of multiplying the first functional constraint by 0. Second functional constraint is multiplied by 1. Third one is multiplied by 0. And the fourth one is multiplied by 4. So I can think of David's solution as multiplying the first constraint by 0, multiply the second constraint by 1, multiply the third constraint by 0, multiply the fourth one by 4, and add them together in order to get that bound. Am I making sense?
Can you add all 4 of them together without multiplying them by 1 and add all 4 of them together?
If you are adding all 4 of them together, you're multiplying each one of them by 1, right? Yeah, you can. But you have to make sure you're getting the objective function on the left-hand side, right? So let's now look at another example. And the question is, can I always do that, right? If I can always do that, then I know how to find upper bounds for Z star. Okay, so then the idea is, let me write down the general LP. Okay, so we call the general let me just use the standard LP. What's the general standard LP? Well, in the general standard LP, you are trying to maximize a certain function, objective function z, which is c1, x1, plus dot 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 Cn xn, right? And subject to certain constraints, and the constraints look like what? A11 x1 plus, and I'm not going to bother writing too much here, A1 and xn, and that's going to be less than or equal to B1, A21 x1 plus dot 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 plus A2n xn less than or equal to B2, and we are going to go dot 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 AM1 x1 plus dot 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 plus AMN AMN xn less than or equal to Bn. Okay, so there are m constraints and decision variables, and of course x1 dot 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 xn, they are all non-negative. Okay, so the question is, how can I get, so how can we get an upper bound? How can we get an upper bound for z star? Okay. And what was the idea that we got from the previous problem is what? What idea did we get at the end? What was the idea that we obtained from the previous example? The way we can get an upper bound is what? Idea is to multiply the constraints if you don't mind, let me maybe I should name the constraint somehow. Let me see. Let me use numbering here. Okay, so let me call this constraint number 1, 2, and then this is the mth one, right? So the idea would be multiply the functional constraints 1 dot 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 m by suitable suitable numbers, let's say y1 greater than or equal to 0 dot 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 ym greater than or equal to 0, and add the resulting constraints to get z, which is c1 x1 plus dot 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 plus cn xn. We want that to be equal to what? If you don't mind, let me do one more thing. I'm going to call the left hand side of each constraint L1, and the right hand side is what? B1, right? So I'm going to think of this as L2 being less than or equal to B2, just so I don't have to write too many things. Is my notation clear? I'm calling the left hand sides of the functional constraints L1, L2 up to Ln. L for left hand side. So I could say that in order to get, I'm multiplying each of the left-hand side by what? Each of the left-hand side, L1 is being multiplied by Y1 plus ... Lm is multiplied by Ym, right? When I add them, I want to get the z function, right? When I add, when I multiply each constraint by Y1 up to Ym, I add them. So the left-hand side will become the z function. And also, this would be less than or equal to, because L1 is less than B1, right? So this would be less than B1 Y1, ... Lm is less than Bm, and then I get this. So the idea is that if I multiply the functional constraints by suitable numbers Y1 through Ym, so that the left, when I add them, the left-hand side becomes the objective function, and then the right-hand side is basically B1 Y1 up to Bm Ym. Is that making sense? So I can get a upper bound for the objective function in this way. Well, this is just an idea, but is this true? We have to know whether this can always be done. Is that clear? Well, let's see an example. I claim that it can't always be done, but we make some progress. Let's look at the following example. Here, I want to maximize z equals to negative 2x1 plus 3x2 plus x3. Okay? And let's say my functional constraints are x1 minus x2 plus x3 less than or equal to 10. 2x1 minus 3x2 minus x3 less than or equal to 10. 6x2 minus 2x3 is less than or equal to 10. And x1, x2, x3, they are all non-negative. Okay, in this problem, can you combine the functional constraints and come up with a bound for the objective function as we did in the first example? You think you can combine them in some way and get a upper bound for the objective function? How did we get the bound again? We multiplied each functional constraint by a constant and added them together to get to isolate the objective function on the left, and whatever the right hand side, that will be the upper bound, right? And I claim that in this problem you actually cannot find any anything that you can multiply all the constraints with and add them together to isolate the objective function. Let's see why. Well, the idea is that you're going to multiply each constraint by some number y1, y2, y3. Let's see if I can find y1, y2, y3 so that when I multiply the constraints by them and add them together, I get the objective function on the left. Is that clear? Alright, so can someone tell me if I multiply the constraints by y1, y2, and y3, add them together, can you tell me what's the coefficient of x1 I get? What would be the coefficient of x1 that I would be getting? Plus I'm going to get certain coefficient of x2 plus certain coefficient of x3, right? And then I'm going to get less than or equal to what? Is my question clear? You're multiplying the first functional constraint by y1, the second one by y2, the third one by y3, adding them together, right? What are you going to get on the right hand side? What do you get on the right hand side? 10y1 plus 10y2 plus 10y3, right? You're multiplying each constraint by y1, y2, y3, right? So on the right hand side, you're going to get 10y1 plus 10y2 plus 10y3. Okay, what's the coefficient of x1? When you multiply the first constraint by y1, you are multiplying x1 by what? What would be when you multiply the first constraint by y1, what's the coefficient of x1? y1. You're multiplying the first constraint by y1, y2, y3, think of them as fixed numbers. So when you multiply x1 by y1, the coefficient of x1 is what? y1. Okay, in the second equation, the second constraint is multiplied by y2, right? So what's the coefficient of x1 when you multiply by y2? 2y2. Okay, plus when you multiply the third one by y3, what's the coefficient of x1? 0. Right? Am I making sense? Can I do the same thing for the other two? Can someone tell me what's the coefficient of x2? The coefficient would be minus y1, okay? Then minus 3y2, minus 3y2, right? And plus 6y3. Is everybody okay? What's the coefficient of x3? Someone else, please? What's the coefficient of x3? y1 minus y2 minus 2y3. Now, what would be the suitable values of y1, y2, and y3? The suitable values of y1, y2, y3 would be such that the coefficient of x1, I want that to be what? I want that to be the coefficient of x1, I want that to be the coefficient of z, x1 and z, because I want to isolate z on the left hand side, right? So I want that to be negative 2. I want this guy to be 3, and I want this guy to be 1, right? Because my goal is to isolate the z function on the left so that I get a bound for that, right? Now, can someone see why I cannot do that? Why isn't there any combination of values of y1, y2, y3 that will satisfy that? Why can't there be y1, y2, y3 for which I get negative 2, 3, and 1 as the coefficient of x1, x2, x3? Yeah.
Can the y value be negative?
No. So this tells you, remember, we want y1, y2, y3, all of them to be non-negative. Why? Because if any of them are negative, then you have to flip the inequality, right? If you flip any of the inequalities, then you get into trouble with what to do. So we want y1, y2. So remember, we want y1, y2, and y3 to be non-negative. So that tells you that y1 plus 2y2 is non-negative, right? y1 plus 2y2 would be non-negative. How could it be negative 2? Right? It cannot be negative 2. Is everybody okay? So our idea that we learned from the first example that, hey, multiply the functional constraints by suitable numbers y1 through ym and add them together, you're going to get a bound for the objective function. It seems like that, well, it doesn't seem like it fails in this example. So what should we do then? Well, is my idea totally hopeless? And the answer is, well, you're almost on the right track, except that so far we ignored something, right? What did we ignore? What information did we ignore in our first example and in our idea? The idea that I have here, what are we ignoring in our idea? We are considering the functional constraints, right? Am I ignoring something? Well, we are ignoring the non-negativity constraints altogether, right? We are saying, let's just work with the functional constraints to get an upper bound, and we totally ignore the non-negativity constraints. So maybe if I put the non-negativity constraints, then I am always going to get y1 through ym. Am I making sense? Is everybody clear? So now my idea will be changed a little bit, and so the idea now is the following. What should I say? Give an amendment to the idea, or what? Okay, so idea that we had before, it was fine, same as before, but also consider the non-negativity constraints, x1 larger than 0, xn larger than 0. Okay, so let me write down the general problem one more time. So in the general problem, we are trying to maximize z, which is c1 x1 plus ... plus cn xn, and subject to a11 x1 plus ... a1n xn less than or equal to b1, and a21 x1 plus ... plus a2n xn less than or equal to b2, and then am1 x1 plus ... plus amn xn less than bm. Now this time we are going to also consider the fact that x1 is larger than 0. I can rewrite that as negative x1 less than or equal to 0, right? The fact that x2 is non-negative, that means that negative x2 is negative, right? Non-positive, right? And ... same thing for negative xn, and that would be non-positive as well. So now we are considering all of them. Now the idea is that we are going to first of all, let me again call the left-hand side of the first constraint L1. So the first constraint is L1 is less than B1, right? The second constraint is L2 less than B2. So I'm calling L2 to be the left-hand side of the second functional constraint, and ... I'm going to take LM for the left-hand side of the mth functional constraint. And then the next one, I'm going to call L m plus 1 less than or equal to 0. And then ... this one would be L m plus n, right? Less than or equal to 0. Is everybody okay? Now, what was my idea? My idea was that multiply each constraint. The idea is that multiply each constraint by suitable numbers y1, y2, ym for the mth functional constraint, and then the rest I'm going to call ym plus 1. Multiply the first non-negativity constraint by ym plus 1, and the second one by ym plus 2, and dot dot dot, the last one by ym plus n, right? You agree? And so what's the idea? That if I multiply them this way, then when I add them together, what do I get? When I add them together, or what do I get on the left hand side? When I add the constraints by y1 up to ym plus 1, what am I getting? Notice that what I'm getting is the following. Let me call this L1 times y1, right? Plus dot 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 Lm times ym, right? You agree? On the left hand side. And what else do I get? I get negative ym plus 1 times x1, right? Minus dot dot dot. And I'm writing out the left hand sides for the other one because it's easy to write them down. And then ym plus n times xn. So basically what I have written down is when I add all the constraints after multiplying by this y1 up to ym plus n, what do I get on the left hand side? And then what do I get on the right hand side? What am I getting on the right hand side? When I add all the constraints together, I'm going to get y1 b1, right? y2 b2, right? Dot 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 yn bm. Do I get anything on the right hand side here? 0. All of them are 0, right? So what am I getting on the right hand side? On the right hand side, I am getting b1 y1 plus dot 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 bm ym, because all the other, for the last n constraints, we get 0 on the right hand side. So this is what I get here. Now remember, what do I want the left hand side to be? What do I want the left hand side to be? I want this left hand side to be what? When I add them together, well, I want them to be z, right? So z, remember, was what? c1 x1 plus dot 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 cn xn, right? And I want to get z on the left hand side when I do that. Is everybody okay with that? You guys are okay with that? Now, I'm going to end here because I have to. I have a doctor's appointment at 2. But what I want you to take from here is that now I haven't really justified why this idea is going to work. That is, now I can actually choose y1 up to ym plus 1, m plus n, in such a way that I do get z on the left. Okay? And I'm going to show you an example next time where we're going to show this idea works. Remember the previous example where the idea didn't work? Now we changed our idea and it's going to work for the previous example. As an exercise, see if you can apply this idea now in order to obtain upper bounds for the objective in the second example. And then later on we're going to show that this idea is going to work. Okay? And this idea is going to give us the dual problem.